histogram is a bar graph, but it's a special type of bar graph. The difference between a bar graph and a histogram is that in a regular bar graph, your bars represent individual pieces of data. So if we're doing qualitative data, it's a single color, a single type of car, a single whatever. And if it's quantitative data, it's a single number, a single age, a single weight, a single height, single data. A histogram is grouped data. It's intervals. So the bars on a histogram represent a range of data, not just a single set of data, or not just a single data point. So, you know, it could represent 0 through 10, 11 through 20, 21 through 30, etc. Now, the bars are known as bins. And the bins is the grouped data. And that's plotted on the x-axis always. Remember we said on the bar graph it's usually on the x-axis, but you could do it on the y-axis and have the bars go sideways. But in a histogram, we always go straight up and down. So the bars always go up. And there's reason for that, and we'll get into that in a second. And then the frequency is on the y-axis. And the frequency distribution is a tool that we use to figure out the data for the bins. How many, the frequency. The bins have no breaks in between the intervals, so when we actually talk about a bin, the first value, the last value of the first bin, so if we go 0 to 9, the next bin starts at 9 to 19. The way this works out is that our first value has a bracket on it, and our last value has a parenthesis. What this means is it includes the first value, but it does not include the last. So in this example, 0 to 9 and 9 to 19, this first one would go 0 to 8.999999999. But any that were actually 9 would not be in this range. It would be over here in the 9 to 19. Yeah, that's the not included part. Yeah. But so it's always bracket on the first, parentheses on the last. So it's 0 up to 9. Like at the very edge of 9, but not 9. And then the next bin is 9 up to the very edge of 19, but not 19. And then the next bin would actually include 19. So it could be like 8.5 zillion 9s and still be included in here. But as soon as you made it 9, it would go into the next one. Does that make sense? No, this is just a parenthesis of an example of how the first value of one is the last value of the one before. This is an example of one kind of histogram, and I kind of glanced over it. The shape of the histogram gives us the shape of the data, and we can also look at the mean, median, and the mode instantly. Because in a histogram, the tallest bin is our mean, our median, and our mode if we're unimodal. Okay, so this mimics a bell curve. Right, because we have that sort of whoosh shape. It's symmetric, or at least close to. So I'm just going to put ish. Symmetric-ish. Okay, there's a single peak. And that's why it's called unimodal. Una meaning one, like in a unicorn, one horn. Okay, the highest peak is the mode. And the median, and the mean. Okay, in a unimodal histogram, so when you have one tall peak like this, and this is a bell-shaped unimodal. We can also have other unimodals, but whenever you have a unimodal, the tallest peak is your mean, median, and mode. So far, okay? We can have a uniform one, where all the peaks are about the same, so you get kind of a flat rectangular shape. And what this means is we have no mode, and approximately all the data is basically the same.
How tall does the mode have to be?
It's, do you see how these are kind of all three the same height and stuff? Like this is mostly the same.
Yeah.
When you have a unimodal, you're going to really have like a peak.
So that one's supposed to be the one down.
Yeah, but it's mostly flat. You're really going to see a peak. No. Yeah, you'll see it. Like, see how this is like a peak, this is a peak, this is flat. So it's really.
Well, I know numbers oftentimes like to go to the gray areas.
Yeah, this one just, you're going to see a real peak on these. Like an actual, like, it's going to go up and down. It's not going to be like flat and then there's one thing and then flat. There will be like a peak. Okay. So all the data on this is about the same. So that was just why it's called uniform. Then you have right skewed. Now, right skewed is taller on the left.
Wow.
And that's because the data is skewed to the right. We have outliers over here on the right-hand side. So it's pulling our data further to the right than it should go. That's why it's called right skewed, but most of our data is on the left. Don't want to use the word bias. What we have is some data over here that, like, this is all the norm. Yeah, the majority of it's to the left, and the abnormal data is off to the right, and that's why it's right skewed. Skewed is pulling it to the right from where it should be. Skewed is not where most of the data is. Skewed is where the outliers are. Yeah. Yes. So the peak is on the left. So just remember, these are opposite from where the name is opposite of where the peak is. So right skewed, the peak is on the left. This is also unimodal though. Right, because we have one peak. So the difference between the bell-shaped unimodal and the right skewed unimodal is the mean is going to be located to the right. Because, right, our mean is our average, and this data over here is going to pull our average away from the tallest peak. So this is still our mode. That's still going to be our mode, but our mean is going to be somewhere over here where this data has pulled it off of the central tendency. So it's the largest value of the mean, median, and mode. Median doesn't have any. So the mean is going to be largest in a right skewed unimodal thing, and it is being pulled right by outliers. Okay, so that's why it's called right skewed. And then our the mode is the tallest peak, and the median will be between the mean and the mode. We don't know exactly where, just looking at the picture, but we can say, okay, we can say definitely this is the mode. We know that the mean is going to be over here somewhere, and that the median is going to be in between them somewhere. But we may not have exact numbers for things, but we can look at it quickly and say some things about it. Everybody got that? And then we can have left skewed unimodal, and you see how, although there's a lot of flat, you can see how there's that definite peak that comes up. Okay, so here again,
So if that one peak
mode.
right there,
Lower.
the one you're pointing at was level, let's say, or in between two next to it, would that mean it's flat at that point, or is that still enough?
Because we have this incline.
Because those three are taller than the rest?
Yeah, so they're inclining. That's what gives you the peak. Yeah, it's like a peak. It's a general mountainy shape. Okay, so here we have the peak is on the right. So again, opposite of the name. Okay, the mean in this case will be located to the left and is the smallest of the mean, median, and mode. So in this case, when it's right skewed, the mean is largest. When it's left skewed, the mean is the smallest. In number, yeah. The median, again, is going to be between the mean and the mode. And again, the reason this is happening, that it's being pulled to the left, is because of left outliers. So that's why it's left skewed. And so when I'm talking about this, I am talking about numbers. And now, if this was a real histogram with like actual scale on here, we'd know what numbers the mode was. Obviously, I can't say, I can say this is the mode. That doesn't mean anything to me because I don't know what the numbers represent. But I know this one's the mode. Yeah, so who knows? But when we have a real one, we'll have numbers and you actually can pull more information out of these. Okay, so far okay? Bimodal. 2 modes. Okay. Yeah, because you can see how there's still kind of 2 peaks. We have 2 modes. The 2 tallest peaks will be approximately the same height. Then it's not going to be bimodal. Because remember, the mode is the number that shows up the most frequently, right? Now, they don't have to be the exact same height. These are not exactly the same height, but they're close enough. You couldn't have like, you know, blah, blah, blah like that, blah, blah, blah like that, and be bimodal. Okay, they have to be almost the exact same height. And again, it's because these are in a number range, so I'll know the ranges, but I won't know the exact count of each number. So that's why we can allow for them to be slightly off. But if I have like peak and then littler peak or whatever, this is still unimodal. That's my mode over there. It's just not symmetric unimodal. Does that make sense? Okay. All right, so we're going to construct a frequency distribution table with a bin size of 10. What this means right here, this is our interval length. Okay, and so what we do is we look and we say, okay, I've got numbers in the 20s, 50s, 60s, 70s. So up to 77 it looks like is my biggest number. I don't have any 80s, so I'm going to start at 20 because I have numbers in my 20s. And so my smallest value will be 20 up to 30, but not including 30. So I don't see any 30s, but if there was a 30 in here, it would not go in this bin. It would go in this one. And then 40 to 50. Hold on a second. I want to write this better. So I've got my bin sizes. What I was saying is if there was an actual 30, Stephen, if there was a 30 up here, which there's not, well, but there is a 40. See how this is 40? 40 won't go here because this does not actually include 40. 40 gets counted in this one. Does that make sense? So I'm just going to, so it's easy to keep track of which row is which. And then all we really need to do is count how many numbers. So 38 is in between 30 and 40, 41, 29, 33, 40. I'm putting it in where the bracket is on 40, not the parenthesis. 74, we're doing this. 66, 45, 60, 55, 25, 52, 54, 61, 46, 51, 59, 57, 66, 62, 32, 47, 65, 50, 39, 22, 35, 72, 77, and 49. So I have 3, 5, 6, 7, 6, and 3. So my bin sizes are over here. That's my interval for my bin sizes. And my frequency is over here. This is going to go on my x-axis, and this is going to go on my y-axis. Okay. Do it again with more numbers. So we've got our bins. Our tally. We have to go up by 5s. So we want a bin size of 5. So that means we can only go up by 5. So I have 0 to 5, the parenthesis, 5 to 10, 10 to 15, 15 to 20. And then my highest number, yeah, so I have to go up to 40. So 20 to, oh yeah, you're right, I'm going by 5s. Wait, there's not a 35, right, just 34? Then I have to go up to 40. Okay, 30, because 30 to 35 does not include 35. So I have to go 35 to 40. No, you cannot. Yeah, it's really important that you can't just make a bracket on the end here. The end is always a parenthesis. Yeah, so 35 will go here, but not here. So as we go through, I've already tallied these, so I'm just going to pretend that we're tallying them as we go right now. So I'm tallying. See, I'm really fast. Uh-oh, what did I just do? I messed up. 11, 9, 12, 14, 7, 10. Are we sure there's a 35? Where's the 35? Oh, right there. Okay. So this is actually going to be like that. Okay, so we have 11, 9, 12, 14, 7, 10, 11, and 1. Okay, and that's where this can be confusing because there might be the desire to stick it in here, and yeah, but we can't because that parenthesis shows me that this does not include 35. 35 has to go into the next bin. Yeah. So just be really careful of that. Those parentheses are really important. So number 5 right here went in this tally, not in this tally. And if there's a 10, this 10 was in this count, not this count. Yeah. So really what you're doing is you're doing 0 through 4.9. If inclusive, but we don't put 4.9 because we're not graphing 4.9s. So inclusive, it goes up through 0 to 4.9 repeating. So that's 0 to 5, not including 5. That's what that's telling us. Okay? All right. So now we're going to use the stuff from A. And we're going to create our histogram. So I'm going to, through the magic of, I did this before already. I have my bins. We were 20 to 30. Not the bins with a D, B-I-N-S. Yeah, I've never been diving. I can't have the bends. Oh, bends with a Z. I thought you said with a D. Well, you guys know what the bends is with a D, right? That's where you're diving and then the pressure sickness thing. Yeah. Yeah. Then I'm going to make a y-axis and an x-axis. And I have my highest frequency is 8. So 8. I have 20, 30, 40, 50, 60, 70, 80. Okay, 20 to 30 is 3, so 3. 30 to 40 is 5, and unlike our bar graph, which didn't touch, our histogram touches. Actually, you know what? I can make that prettier. But see, I'm not touching. I have to fix that. Our histogram has to touch. And then 6. Up here? Ah, that's a good idea. 8. 5 again. And 3. Oops. I pulled it back when I was going. Now, technically speaking, I'm not really doing this correctly because you see how my rectangles are different widths? It does. But all of these bins our widths should be the same. So if I made a correct scale on the bottom, these would all be the same width. So graph paper comes in handy for that. And then what I usually do is something like this, just to differentiate, to help it, stand out which bars are which or something, or color them in with different colors, something like that. And this is our, so I can tell you we have a unimodal, right? We have single mode, single peak. It's relatively symmetrical, so this is going to be our mean, our median, and our mode. Now, if I'm asking you what is the exact mode, we don't have a number. We're between 50 and 60, so we pick the midpoint, 55. 55 would be our mean, our median, and our mode. Okay. The question here is what percentage of the winners are 50 or older? Well, here's our frequencies. There's 30 people total. Okay. Yeah. So that's 8 and 8, which is 16. So we have 16 out of 30, which gives us 0.53 repeating. So 53% of our data is age 50 or older. Now when we look at that, 53% of our data is age 50 or older. 55 is a really accurate choice for the mean and the median and the mode, the middle of the data. Yeah. So does that make sense? Okay. All right, so here we had the teachers from the first example. So we're going to make a histogram on that. And you know what I'm going to do? All right, so we had our data. So remember our bins were 0 to 5. And our frequency on that was 11. And then we had 5 to 10. And our frequency was 9. And 10 to 15 gave us a frequency of 12. And 15 to 20, we had a frequency of 14. 20 to 25, we had a frequency of 7. Did I write that down right? Oh yeah, that's right. And then 25 to 30, we had a frequency of 10. 30 to 35, 11, and 35 to 41. Okay. Now, I need to figure out how wide to make this. I've got 1, 2, 3, 4, 5, 6, 7, 8 bins. So if I make them too wide, I would have to go across 16. So I just want to make sure I have enough room for that. So, wow, I can't even make a straight line when I have a straight line. No, it's not their ages. It's the number of years of service for the teachers, yeah. So it is, the ages were on the other chart. Okay, so here's 0 to 5, 10, 15, 20, 25, 30, 35, 40. That's wide enough, so we've got plenty of room. As a matter of fact, I'm going to shorten it a little and then put the numbers in. And up the side, we're just going to go by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which our highest was 14, so we're good there. Our rectangle going. And I have 11 here. I should have touched. And then 9. 12. 14. 7. 10. Was that 11? Yeah, 11. And 1. Okay. So how many teachers teach in the small town? Well, the answer to number or letter I, we'd add up the total number of all of the numbers that we had in our frequency. So we total that up and we get 75. So 75 teachers. How many have worked for less than 5 years? Well, that's this bin right here, because it doesn't include 5, right? So it's for less than 5, so that was 11. If they're able to retire when they've taught for 30 years or more, how many can retire? Well, here's over 30 and more, so I've got 12. It should have been 11. I made that too tall. Okay. I have 11 plus 1. So that's 12 teachers can retire right now. And then what percentage of them have to teach for 10 years or less before they can retire? Now they have to teach for 30 years or more. So to teach for 10 more years or less is between the 20 to 30 range. So that was 7 plus 10. So that's 17 of them out of the entire 75, which would give me 23%, can retire within 10 years. So any questions on that? Not too bad? To histograms. A frequency polygon is a graph, like everything else in this chapter. But we construct it by using lines to join the midpoints of the intervals in a histogram. The heights of the points equals the frequency. Now to calculate the midpoint, we take the two sides of the intervals. So you add the two sides of the intervals. And divide by 2. So if your bin was 0 to 5, you take 0 plus 5, divide by 2, so your midpoint would be 2.5. Now we are going to create a frequency polygon from this histogram. Okay, so what we do is we find the midpoints. Okay, so 20 plus 30 divided by 2, that's 50 divided by 2, so that's 25. And then 30 plus 40 divided by 2 is 70 divided by 2, so that's 35. And then 40 plus 50 divided by 2 is 90 divided by 2, so that's 45. And do you guys see the pattern? Okay. There will be a pattern, and it will become apparent pretty quickly in these because the bins are all the same size. So your midpoints are going to match a pattern. So we make a dot. At the top of each of these peaks in the middle. Yes, and then we connect the dots. Now, we have to go a little further than just connecting the dots. We come down to the midpoint of the interval on each side where there's no data also. Okay, so then we connect the dots. To give it a beginning and an end that's not just dangling off in space. Now this will not be a curve. You make individual straight lines to connect it so that it's zigzaggy or jagged or, yeah, or a Christmas tree. Really bad Dr. Seuss Christmas tree. Okay, and then once we've connected the dots, okay, put dots on midpoints. We put the dots on the midpoint at 0 frequency on each side at the bottoms, and then connect with straight lines. Okay, so be really careful. You don't like try to curve. It's straight lines. If you're creating a frequency polygon, you will leave space unless your first bin starts at 0. If your first bin starts at 0, what you would do then is, let's say here's your first bin and you put this dot here, you would come to the 0 on the edge. Okay, but that's the only time you won't go to the midpoint. And then on the side, you just always add another interval, and that's okay. So if you start at 0, connect to 0, 0. If you don't start at 0, leave a space before it if you're creating a frequency polygon. No, on the other side, you can just add another space always. So you always go to the midpoint on the other side. Okay. So here we have a bin. On these, I don't know why it copied off as colons. They're supposed to be 5.5, 10.5. Here, I'll fix it real quick. There, that makes it look more like actual, numbers. It's not times, it's miles. There, okay. All right, so we are going to create a frequency polygon for this. We are not going to create the histogram first. You don't have to make the histogram to make the frequency polygon. So I'm going to pull in some graph paper again really quickly. Hold on one. So for this one, I'm going to go by 2s. So 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 32, 4. Yeah, it'll be good. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. I don't need to go any further than 40. Okay, anyway. I need to find the midpoint. Okay? So the midpoints, I have 5.5 plus 10.5 divided by 2. So this is 16 divided by 2, so that midpoint's 8. So I'm going to write the midpoints here. And then the next midpoint would be 10.5 plus 15.5 divided by 2, 26 divided by 2, 13. And then 15.5 plus 20.5 divided by 2, so that's 36 divided by 2, which is 18. Plus 5 plus 5 plus 5. So 13, 18, 23, 28, 33, and 38. Those are my midpoints. My frequency is 1, so on 8, I'm at 1. Okay. On 13, so 12, 13, so halfway through here, I am at 3. 18, I'm at 2. 2, 4, 6, 8, 10, 12. I'm one line over. Sorry. That should be there. That was too close. 12, 14. So 10, 12, 14. Sorry. 18 is 2. 22, 23 is 4. 28 is 5. 33 is 3. And 38 is 2. You're right. Thank you. Now, I have to go to the midpoint of the interval before. Right? So the interval before 5.5 would have been 0 to 5.5. and that would be 2.75. So I'm going to come over here close to 2 and just put a dot. And then on the other end, it would be 40.5 plus 45.5 divided by 2. So that would have been plus another 5. So yeah, 43. So I'll put a dot here. So if I had put the bars in, we would be in the middle of the top of the bars. But see, I don't have to actually put the bars in to make the line. Yeah, this is called a frequency polygon. Yes. Yes, that would be a mode here. Now, what all this tells us is the frequencies of the numbers in that general area. So, yeah, so like there's in this general area at 30 or at 28, there's, about 5. So it gives us a kind of a really quick visual of how many of things there are. That's all it really does. So far okay? Now, on the next page, we have the heights of professional basketball players. So, we can figure out how many players' heights were measured because we have frequencies. So I have 6 plus 9, plus 10, plus 22, plus 24. Okay, so 6 plus 10 plus 22 plus 24 plus 16 plus 20 plus 2. Okay, 100 players were measured. What is the bin size on which it is based? This is the midpoint. So I've got between 69 and 72 are my other 2 points. So my midpoint is in the middle of some middle here and here. So between 66 and 69 I have 67 and 68, right? So my halfway point is going to be 67 and a half. And halfway over here I have 70 and 71, so halfway between is going to be 70 and a half. And it's asking us, what is the bin size? 67 and a half, 68 and a half, 69 and a half, 70 and a half. My bin size is 4. Does that make sense? Oh no, I'm lying. It's 3. Yeah, it's 3. I counted wrong. So my bin size is 3 inches. Okay. What is the height? What range of heights is the most common? Okay. Most common. Well, we've got the halfway thing, right? So 76, 77, so 76 and a half to 79, 80, 79 and a half. Huh? If I look at what? No, this one is, no, it's saying what is the most common height. So the most common height is going to be the one with the most people. Yeah, 78 is the most common. 78 is the most common. This is what range of heights is the most common. And 78 is the midpoint between these two. So remember there's 76, 77, 79, and 80. And halfway, so 76 and a half to 79 and a half is our, that's okay. So that's our range. Did that make sense? Did that make sense, the range thing, guys? Everybody else? Yeah, okay. Okay, what range of heights is the least common? Whoops, wrong direction. Okay, we can't count the zeros, right? Because those get added on at the end. So this height right here is the least. So yeah, so we have 85 and a half. And 88 and a half, yeah. Which is really tall. I mean, if you, okay, because we're going inches, right? 6 feet is 72 inches. 7 feet is 84 inches. So this person, sorry, there was what, 2? Yeah, these 2 people are over 7 feet tall. That's very rare. That's why there's not very many of them, right? And then if you look at this, the most common height is 78 inches. That's 6.5 feet. That's pretty common for a professional basketball player. Like, you know, there are very few short ones. All right, which percentage of the basketball players had a height of less than 76.5? I keep going the wrong direction. Okay, here's 76.5. So I have 22 plus 10 plus 6. I can't seem to go in the right direction. So that's 38 out of 100. So 38% only are less than 6.5 feet. Oh, well, 6 and 4.5 inches, 6'4". So only one, like, you know, like not even a fourth of players. No, I'm sorry. A fourth would be 25. Just over a third of players are under 6'4". That's a frequency polygon. Not too bad? Okay, so your homework assignment